this section is really a summary section of the past several sections that we've been looking at in Chapter 4. And so this section is talking about curve sketching. In general, how do we sketch the curve of a function utilizing all of the tools that we've talked about? Well, going back even beyond just Chapter 4, going back all the way into when we talked about vertical and horizontal asymptotes. So just really taking all of the knowledge that we've learned about graphing functions through pre-calculus and now calculus, how do we pull that all together to create a very accurate graph of a function, to really give all the information about a function, all the important information about a function and how it behaves graphically. So just some basic guidelines for curve sketching. What we're going to do, so I'm going to outline the guidelines here and then we're going to go through some examples and really spend the videos for this section just practicing all of these techniques and getting experience graphing functions utilizing all these tools. So guidelines for curve sketching. First thing we're going to do, find the domain. So, obviously we need to know the interval that we are looking at, or intervals that we are looking at a function. So determine what the domain of the function is. So that's the first step. That goes way back into pre-calc stuff. But that's our first step. Figure out what the domain is, or if it's a restricted domain, right? Consider what that restriction means. Then find the intercepts if possible, and I am going to just leave this a little bit open. Normally finding the y-intercept is pretty easy if it exists, because we can just plug in x equals 0. Finding the x-intercepts sometimes are easy, but sometimes it's more difficult. And so we won't hold fast that we have to find all the intercepts, but if possible, it's good to find the intercepts. They give us some additional information about the curve that we can use. If it proves to be too difficult without some advanced estimation techniques, then we'll find just what we can. Then going back into pre-calc a little bit as well, determine if the function has any symmetry or if it happens to be periodic. If it's like a trig function would be a good example of a periodic function, something that cycles through the same graphical characteristics every so often, every p, a period of p. So these are, of course, just the definitions for an even function. Oops, started moving the screen. For an even function, if f of negative x is equal to f of x, like x squared or cosine of x, an odd function, f of negative x equals negative f of x. And if we know that it's even or odd, it has some nice symmetry that can be used when graphing it. Even functions are symmetric across the y-axis, odd functions are symmetric through the origin, and then of course the periodic nature. So if we have a periodic function, meaning that it cycles every I'm calling the period here p, so it cycles through its period or repeats through its through a period of p. Like sine of x or tangent of x, like the trig functions are good examples of periodic functions. Okay, so that's really kind of pulling from the pre-calculus knowledge. That gives us a baseline to get started. Oh, by the way, not all functions, in fact, most functions are not symmetric or periodic, but this is just a good thing to check as we're going, kind of like the intercepts, right? We do a quick check. If it's obvious that it has symmetry, that can be useful in the graphing. Okay, then we get into our calculus tools that we've worked with. So find all of the asymptotes of the function. So the next thing we want to do is we want to find all the asymptotes of the function. This goes into vertical asymptotes, horizontal asymptotes. So remember, our vertical asymptotes are the asymptotes where we have infinite behavior around some line x equals a. This is where we're going to be considering the denominator, the domain of the function, and determining where we have those that behavior where the function approaches infinity or negative infinity, where we have infinite behavior for the function about a vertical line. Then we have our horizontal asymptotes we want to check for, and this is where we're going to take the limit as x approaches both positive and negative infinity and see if there's horizontal behavior that can be captured. And then we have something new that we'll talk about in this section, and that is the slant asymptotes. And so we'll go through that after we've done a couple examples. So a slant asymptote is where we're actually approaching some line, a linear line that is not horizontal, actually, I guess to be specific, because that would be a horizontal asymptote. A slant asymptote is when you have, if I could just draw like a very brief little picture here, it's when you have a function that maybe does something like this. Put in a vertical asymptote there too. where it's actually going to approach a line, y equals mx plus b, as we approach infinity or negative infinity. That's what we call a slant asymptote. And we'll talk about a specific types of functions that have those. Very specific rational functions will have slant asymptotes that we can explore pretty easily in this section. So we'll look for all those asymptotes. That's the fourth step. The fifth step then gets into more of our calculus, where we're going to actually look at the sign charts for the first derivative. So we take a first derivative sign chart to figure out where does the function increase, decrease, where does it have local or relative maxes or mins. So this is really, we've been working with this for the last couple of sections and continue to do this when we're graphing. Figure out the intervals on which the function's increasing, decreasing, and then get in there and say, okay, if I know that the function increases, decreases, and my critical point happens to be, I'm going to just make an assumption on this generic one I have here that this was actually a horizontal tangent. And if we know that the function increases till it gets to a horizontal tangent and then decreases, that's going to make that a max. Okay? So we can pull a lot of information off of that sign chart. So we'll create that sign chart for our functions when we're graphing them. So that's the fifth step. Then the sixth step is to look at the second derivative. So now we take the second derivative and we determine where the function is concave up, concave down, and where it has inflection points. So again, we make another sign chart, figure out where is the function going to change concavity, what intervals is it concave up, what intervals is it concave down, and utilize that information to further, fine tune the graph of our function. And then Step 7 is really just about putting it all together. So put it all together and actually graph the function. That's our last step. I always start by, plot all your asymptotes. That gives you kind of a skeleton of the graph. Then plot all the points that have been found. You can label maxes, mins, inflection points. When you're plotting all the points, you do need the ordered pairs. And so for this step, it might help to make, in this last step, to make a T-chart of ordered pairs. So this might be a good time to make a T-chart of ordered pairs so that you can plot all those points and actually have them to scale. Then get in there and actually sketch the graph with the asymptotes, the points, use those to guide the graph, use the increasing and decreasing intervals, the concavity, make sure that you get that really nice fine-tuned graph of your function utilizing all the information. So it's really good practice. I know that we can go to, obviously, our graphing calculators. I know we can go to Desmos and we can get more accurate graphs than we can actually do by hand. But this is a time to really practice all the skills that we've learned in calculus. And so make sure that you know how to do these all by hand. Make sure that you can go through this process and you can do this all by hand. Or that you could take, even not given a function, just given the information, those formula graphs that we look at. Make sure that you can take those formula graphs and create a very accurate graph of a function that meets all the criteria given. Okay, so now I want to just spend some time. That is the content of this section, aside from just a little more on slant asymptotes in the second video. So now I just want to spend some time getting into this process of going through this, graphing it, finding all this information about a specific function. So let's do that for our first example. So here's our first example. Let's graph the function y equals x times e to the negative x squared up here in the right corner of the screen. So I want to graph that. What I did over here was I just listed out those 7 steps. I had very specific details in my earlier screens about what it means to do each of these things. Here I've really just summed them up in as little words as I could to summarize those steps. So here's the steps that we're going to go through when we're graphing. So the first thing we're going to do is we're going to look at the domain. So what is the domain of the function? So over here I'm just going to write out the steps as we do it. So what is the domain of this function? So the domain for this particular function is it's x. It's a linear function x times an exponential, where the linear function and the exponential have no restrictions on their domains. Therefore, the domain of this function is from negative infinity to infinity. And then let's think about intercepts. So if we wanted to find the intercepts, well, let's try plugging in x equals 0. So if we do x equals 0, y is going to be, what would be the y-intercept? That's just going to be 0 times e to the 0, which is 0. So we know we are going to pass through 0, 0. Okay? Now, that's so obviously that was the y-intercept. I didn't like that, but that was the y-intercept. So we've got the y-intercept. So we've got our domain, we've got the y-intercept, we've got one point that we know that we're going to have. And then for the x-intercepts, this is one where it's actually maybe not going to be that difficult to find. So what would be the x-intercepts when y equals 0? So I could have put a little arrow here. I'm going to zoom in because this is pretty small. So for the x-intercept, when y equals 0, 0 equals x times e to the negative x squared. Well, that's going to occur when x equals 0, or, so we already actually know one of the x-intercepts at least, negative e to the negative x squared equals 0. But this cannot happen because exponentials, by the way, e to the negative x squared is greater than 0 always. And exponential is always greater than 0. So there's no roots from that one. There's no possible x values from that equation. So it's really just this 0, 0. So it's really, well, we already wrote it, so I'm not going to write it again. So 0, 0. I said I wasn't going to write it again, then I did. But we already highlighted it. So there's really only one intercept. It's only going to cross the x and the y-axis at the one place that you can cross them both at the same time, which is the origin. Okay, so find the intercepts and then consider symmetry. So then we could consider symmetry. So if we wanted to consider symmetry, by the way, this is not a periodic function. There's nothing about either of those functions that is periodic, so I'm not even going to think about that. But I am going to pause for just a second and think about some symmetry. So let's think about symmetry. So let's consider, to do that, let's consider what f of negative x might be. Called this guy y equals x e to the negative x squared, but we could think of that as, of course, f of x equals x e to the negative x squared. So what would be f of negative x? So f of negative x would be, plugging in negative x everywhere there, would be negative x times e to the negative x quantity squared. But that's going to be negative x times e to the negative. When you square the negative x here, it becomes just x squared, but there's this negative on the outside. So you've got negative x squared. And notice that that is actually negative f of x. And by definition, if you plug in negative x and you get back the opposite of the original function, negative f of x, so if you plug in negative, that is by definition a odd function. So that defines an odd function. So we are an odd function, which means that we are symmetric about the origin. If you need a visual, just think x cubed. X cubed is an odd function. And so this graph will be symmetric about the origin. Okay. So that's useful. That can help us a little bit when we're graphing and plotting points. Okay. Okay. So we've done all of the pre-calculus things here. We've got the domain, the intercepts, the symmetry. Now let's head into a little bit of calculus. So now let's think about the asymptotes. Already talked about the domain, so there's not going to be any vertical asymptotes. We are not going to have infinite behavior because we are defined across the entire number line. But what about horizontal asymptotes? So let's consider that. So there's no, the fourth step is to look at the asymptotes. And there are no vertical asymptotes. And my reasoning here is, of course, like we are just defined on the real numbers from negative infinity to infinity. So no vertical asymptotes. But what about horizontal asymptotes? So horizontal asymptotes, we have to consider the limit as x is approaching positive and negative infinity of x e to the negative x squared. So what occurs as we approach positive and negative infinity here? Let's go ahead and just do positive infinity first, and then we'll come back and look at negative infinity. So when you're doing the horizontal asymptotes, you do have to check both. Just because you have a horizontal asymptote on one side of the graph doesn't mean you necessarily have the same horizontal asymptote or even have a horizontal asymptote on the other side of the graph. So make sure you always check from both sides of the graph for those horizontal asymptotes. So as we approach infinity, by the way, this is going to become, this is where we get to utilize some limit techniques, because this becomes infinity times, notice that e to the negative x squared is 1 over e to the x squared. So that's actually 1 divided by infinity, or infinity times 0, which is indeterminate. This is one of our indeterminate forms. So this is an indeterminate form, which means that we can utilize L'Hopital's rule, but not in this form. We got to do a little bit of work, but here we already have the reasoning, the work that we're going to do here. We're just going to drop that negative exponent down to create a quotient. So this is going to become limit as x is approaching infinity of x over e to the x squared. And that, of course, is infinity over infinity. And that is indeterminate, but in that form, I can apply L'Hopital's rule. And that's what I want to do. So to take this limit, this is where we're really pulling all, again, this is a real summary section here. We're pulling all of the skills that we've learned together. So we'll take the limit. When we apply L'Hopital's rule, we take the derivative of the top and we take the derivative of the bottom. And then we simplify. There's not much to simplify here, so we reevaluate. And when we reevaluate here, this becomes 1 over infinity, 1 over a quantity that is growing without bound. We've got infinity times infinity, that becomes infinite, and therefore this is approaching 0. And that is a horizontal asymptote. So it's giving me one of my horizontal asymptotes. So we had no vertical asymptotes, but so far on the horizontal asymptotes, I'm going to summarize them up here. We have y equals 0. So far we have y equals 0. By the way, this did approach positive infinity. And so either way, positive or negative infinity right here, when we take 1 and we divide, this is going to approach 0. In this case, it's approaching 0 from a positive direction. So, might be worth thinking about putting in that directional sign there if we wanted to. Okay, now we also have to consider, we did positive infinity. Now we just have to essentially run this exact same thing, but with negative infinity. And I'm going to skip a few steps on that one and start with x over e to the x squared. That is going to be a negative infinity over infinity, which is indeterminate form, but I can apply L'Hopital's rule. Make sure you show that it's in the proper indeterminate form. Then you can apply L'Hopital's rule. Also show that you're applying it with some sort of notation. Limit as x approaches negative infinity of 1 over, it's going to be the same thing we had before, e to the x squared times 2x. This time when I evaluate that, it's going to be 1 over, in the bottom we have infinity times negative infinity. So it's actually going to be decreasing without bound, 1 over negative infinity, which will approach 0, but from a negative direction. So 0 from a negative direction there, but that is, not necessary, right? I mean, I am putting the directional signs on these just to be very concise here, but those are not necessary. We could just say that we're dividing by infinity or positive infinity, and negative infinity or positive infinity, and that will approach 0. So we have that one horizontal asymptote and no vertical asymptote. So we have no vertical asymptotes for this function, and we have one horizontal asymptote on both sides of the graph. This is as, we should add that in, because sometimes we could have a horizontal asymptote on only one side. So this is as x approaches positive and negative infinity. So let's add that into my highlighted conclusions there. Okay, once we've done all that, so now we've done the asymptotes. Now what we want to do is we want to then take the derivatives. So remember, we've got, let's get it all on the board here. So we've got domain, intercept, symmetry, asymptotes. Now we're going to take both the first derivative, and we're going to do steps 5 and 6, where we take the first derivative, determine intervals of increase, decrease, local maxes and mins, and then we're going to find intervals of concave up, concave down, and all inflection points using the second derivative. So let's start with the first derivative. So step 5. So we're going to look for y prime sign chart. So y itself was x times e to the negative x squared. So y prime, we got to use product rule, is going to be 1 times e to the negative x squared plus x times e to the negative x squared times the negative 2x. Just doing a little simplification here, let's pull out e to the negative x squared, and we're going to have 1 minus 2x squared for my derivative. So there's my derivative. I got to find the critical points. So we would look at where e to the negative x squared times 1 minus 2x squared equals 0. So that would be when e to the negative x squared equals 0, but that's never equal to 0 because e to the negative x squared is greater than 0 always. Okay, but when does 1 minus 2x squared equal 0? Well, that's going to equal 0 when x squared equals 1/2, or when x equals plus or minus 1 over root 2. If we prefer plus or minus to rationalize, root 2 over 2, which is approximately, and I do think for the sign charts it helps to have the decimal form. Okay. All right, so now let's make the sign chart. Negative root 2 over 2, positive root 2 over 2. Looking at the sign of y prime here, and if we look at the sign of y prime, notice that this, in our derivative here, this quantity here is actually always positive, times 1 minus 2x squared. So we're really looking at the sign of that second piece. So positive, if I pick something to the left of negative 0.707, negative 5, for example, this is going to be negative. So this results in a negative, and this is decreasing on that interval. If I pick something in the middle here, like 0, I'm going to get a positive times a positive, which is a positive. So that's going to increase. And then I'm going to have a positive times, pick something over here like positive 5. And so that will be 1 minus 2 times 25. So negative, result in a negative, and be decreasing. We also know that at each of these 2 points that we have a horizontal tangent. So I'm going to abbreviate HT right here for horizontal tangent. So we are decreasing. So in terms of what this graph is going to look like, we know that we're decreasing. We don't know the concavity yet, but we know that we decrease, then we increase, then we decrease again, which is going to make this point and this point local extreme values. This is going to be a minimum, and this is going to be a maximum. So kind of getting a little bit of a sense as to what's going to happen there. I'm going to go ahead and put step 6 right next to this, where we look at the second derivative sign chart. And for the second derivative sign chart, y prime was equal to e to the negative x squared times 1 minus 2x squared. So let's go ahead and take the second derivative from that. So we will have to apply product rule there. So e to the negative x squared times negative 2x times 1 minus 2x squared, plus, and then we're going to have e to the negative x squared times the derivative of the second function, 1 minus 2x squared, which is minus 4x. And then just utilizing some algebra here, I see a common factor of negative 2x. I want to get this cleaned up. So I'm going to pull a negative 2x. I also see an e to the negative x squared I could pull out from both of those terms, which would leave me with a 1 minus 2x squared from the first term, plus on the second term, since I pulled out a negative 2x and I pulled out the e to the negative x squared, all that's actually left there is a 2. Okay. And so my second derivative cleans up pretty nicely into negative 2x times e to the negative x squared times 3 minus 2x squared. So let's find the second order critical points from this function. So let's consider when does negative 2x times e to the negative x squared times 3 minus 2x squared equal 0. Oh, we also need to consider where these are undefined, but these functions are not ever undefined. These derivatives, I don't think I even mentioned that on the first derivative. The first derivative is actually defined. Here it is right here. The first derivative is defined for all values, so I only looked at the equals 0. Similarly, I'm only looking at the equals 0. This second derivative is defined across the entire number line. Remember critical points, though, you do also want to consider where the derivatives are undefined. Okay, so now we're going to set these equal to 0. So negative 2x equals 0. That will give me 0. The second factor here, e to the negative x squared equals 0. Never, because e to the negative x squared is always greater than 0. And then when does 3 minus 2x squared equal 0? Well, when x squared equals 3 halves, or when x equals plus or minus the square root of 3 halves, or the square root of 6 over 2 plus or minus, which is approximately, because again, it's helpful on our sign charts and when we go to plot, plus or minus 1.22. Okay, just plugged that into the calculator and wrote that down ahead of time. So now let's actually make the sign chart. So the sign chart for the concavity, to figure out where we're going to be concave up, concave down, take our sign chart, take a chart, look at the sign of the second derivative, take our critical points, so we have 3 of them, second order critical points, 0, and then we've got over here, we've got negative root 6 over 2, and we've got positive root 6 over 2. Remembering that this is negative 1.22, and this is positive, approximately positive 1.22. Okay, so looking at the sign of these, we can pick something on each interval. We can do a test point. We're taking negative 2 times e to the negative x squared times 3 minus 2x squared. So as I'm plugging in values, so if I were to test in, say, negative 5, okay, pick whatever you want, pick negative 5. So if I plug in negative 5, I get a positive. E to the negative x squared is actually always positive, so positive, and then if I were to plug in negative 5 here, I would get 3 minus 50, so that's negative. So this means we are definitely concave down on this interval. Then something between, if I were to pick something like negative 1, I'm going to get a positive and a positive, and if I were to plug negative 1 in here, I just get 3 minus 2, and that's positive. So this is positive, which means I'm concave up on this interval. Let's go ahead and pick positive 1 on this interval from 0 to 1.22. If I pick positive 1 there, I'm going to have a negative times a positive times a positive. So that's actually a negative. So we're concave down. And let's go ahead and pick something like positive 5 over here. I would get a negative times a positive times a negative, which gives me a positive, and we're concave up. Okay? Which means at each of these points, we have an inflection point. Each of these are places where the concavity changes. So these are each inflection points. Okay. All right. Whew, that's a lot of information. Okay? These are summary examples. These are, we are pulling together 2 whole chapters really, all of our limit behavior as well as some pre-calculus stuff. So we are pulling together a bunch of stuff on these. Okay? I have the graph right here. I actually pulled it out of Desmos, but I'm going to hide it for a second because we can create that graph without any technology. Actually, we haven't even used any technology aside from to estimate our ordered pairs. So now we're actually going to plot some points. And in order to plot some points, I mean, we know we've got 0, 0. So I can plot 0, 0 right here. But I also have all of these first order and second order critical points. I know that I've got a min and a max and 3 inflection points, but I don't know exactly where to plot them on the graph. So in order to plot them on the graph, I think it helps to have a little t-chart. So I'm going to go ahead and generate a little t-chart over here. I'll speed up the graph as I'm generating the t-chart and plotting the points. But that's what I'm going to do next. I'm going to actually, so this is step 7 where we're actually graphing the data. So we're actually going to graph using all info. Here's where I find it useful to create a little t-chart just to get all of my ordered pairs, because I know the x values for all those critical points, but I now need the y values in order to graph them. So I'm going to go ahead and do that now. Okay, so here we have the graph with the inflection points labeled, the min, the max labeled. I filled in the ordered pair. I find the ordered pairs in a little T-chart. I find that a little bit easier just to organize the data. And then we can jump over to the graph and we can see what it looks like and label our mins and our maxes and really pull everything that we've done together into a single graph and use all that information and where it's increasing, decreasing, where we've got concavity, concave up, concave down. We also have the horizontal asymptote in here. You can see that this function on both ends of the graph, both sides of this graph are approaching zero. From that vertical asymptote, we've got our intercept. We've also got the symmetry here, and we can see it all. And if we were to grab this graph out of Desmos, the same graph, and I've zoomed in a little bit when I did it in Desmos here, but we can see that same graph right here. We can see the same behavior general graph, but we have a very accurate graph utilizing all this information. So remember, of course, we have access to graphing calculators and graphing tools that can generate these graphs for us. But remember, this is really a summary section, practicing our derivatives and our limits with the asymptotes. And can we take first order derivatives, second order derivatives? Can we gather all the data about where functions are increasing, decreasing, where we have maxes and mins, and where we're concave up, concave down? All of that behavior, and can we label graphs correctly and generate all the information about the graph without a tool. So utilize your technology, utilize your tools with technology, with graphing calculators and Desmos, but do it after you've done the hard work, after you've done the practice and summarized all your knowledge. Then go and check your work. So here we have it, a nice summary example.